Alright, thanks for watching. And today I will show you 10 examples of limits at infinity so you can see which method to use for which problem. So let's start with a very easy one, which you'll see will never happen in your life, unfortunately. Let's start with the limit as x goes to infinity of 1 over 3e to the x minus 2. Well, this one is not too bad. You just plug it in. So it becomes 1 over 3e to the infinity, which is infinity, minus 2, and that's 1 over infinity, and that's 0. As I said, unfortunately too good to be true, we would usually ask you slightly harder questions, which leads me to the next one. How about the limit as x goes to minus infinity of 3x cubed plus 2x squared plus 4x? So this is a polynomial, and a good method to use for polynomials is simply to factor out the highest power. In this case, x cubed. So this becomes the limit as x goes to minus infinity of x cubed times 3 plus 2x squared over x cubed plus 4x over x cubed, which becomes the limit as x goes to minus infinity of x cubed times 3, and then this simplifies to 2 over x plus 4 over x squared. And then let's see what this becomes. So as x goes to minus infinity, this becomes minus infinity cubed, which is still minus infinity. And this thing we get 3, and then 2 over a very large negative number becomes 0. And then 4 over a large negative number squared, that's 4 over infinity, and that's 0. And then what you get, it's simply 3 times minus infinity, and 3 times a very large negative number becomes a very large negative number. So it's minus infinity. And by the way, always make sure to check if your answer makes sense. Well, the ideas for this polynomial, all that matters is the leading term. So what you should get is roughly 3 times negative infinity cubed. But a negative number cubed is always negative. So you should expect a negative answer here, which we have here. All right, so that's for polynomials. And well, you may ask, what about ratios? So let's try to deal with this example. Limit x goes to infinity of x squared minus 4 over, I think, x to the 4th plus 3x squared plus 1. And by the way, that is very interesting because usually for limits at a point, a good idea would be to factor out, let's say, the numerator as x minus 2 times x plus 2. This is completely useless for limits at infinity. So the techniques for dealing with those are completely different from the techniques for dealing with limits at a point. Namely, what you do with ratios, in this case, you factor out the highest power of the numerator and the denominator. So kind of like a generalization of this. So you get x squared times 1 minus 4 over x squared. And this one, x to the 4th times 1 plus 3 x squared over x to the 4th. So 3 over x squared and 1 over x to the 4th. So you have that, and there should usually be a simplification here. For instance, what happens here is that the x squared cancels out with the x to the 4th, and what remains is another factor of x squared. And then what you get is the limit as x goes to infinity of 1 over x squared, 1 minus 4 over x squared, and 1 plus 3 over x squared plus 1 over x to the 4th. And let's see what this becomes. So this is 1 over infinity, basically 0, times 1 minus 0 over 1 plus 0 plus 0. This becomes 1 times 1 over infinity, which is 0. So in the end, you're left with 0 times 1. And that is not an indeterminate form. 0 times 1, it's, just from multiplication, that is just 0. Just like saying 2 times 0 is 0. That's also fine. The problematic situation would be 0 times infinity, because then that's indeterminate form. Okay, so for rational functions, very good to factor out the highest power of the numerator and the denominator. Well, it turns out there's a similar technique for other kind of ratios. So let me do this one, which was actually on an exam in Berkeley. So the limit as x goes to infinity of ln of x squared plus 1 over ln of x squared plus 3, or maybe the opposite, just to make sure. So ln of x squared, and what was it, plus 3 and then minus 1. You'll see it won't really matter. Well, if you think of this as x squared plus 3 over x squared minus 1, you would be like, let's factor out x squared. Well, it's the same thing here. Let us factor out this ln of x squared term and see what happens. So that becomes the limit as x goes to infinity of ln of x squared, and then 1 plus 3 over ln of x squared, and then ln of x squared, and then 1 minus 1 over ln of x squared. And then lo and behold, notice what is happening. The ln of x squared terms cancel out, and you're left with simply the following limit as x goes to infinity of 1 plus 3 over ln of x squared over 1 minus 1 over ln of x squared. And then what this becomes, it's simply 1 plus 3 over infinity, because ln of x goes to infinity as x goes to infinity, and then 1 minus 1 over infinity, which just becomes 1 plus 0, and then 1 minus 0, and that's just 1. Which again makes sense. As x goes to infinity, ln of x becomes huge, much bigger than this 3 and much bigger than this minus 1. So in the end, the limit should be 1. Okay, now moving on, what happens when you have a square root? There's a bunch of interesting things that's happened. So, for instance, let's do the following. Limit as x goes to minus infinity of x plus 2 over square root of 9x squared plus 1. Okay, if you see just a square root and not square root of something plus something, the technique is just to factor out the highest power from the square root. So what we would like to do is as follows. So from this square root of 9x squared plus 1, what you want to do is factor out x squared. So this becomes x squared and 9 plus 1 over x squared. And well, we still have a ratio, so don't forget about your other techniques. For the ratio, also factor out x here. 1 plus 2 over x. And then what you get is limit x goes to minus infinity of x times 1 plus 2 over x. And then square root of x squared, square root of 9 plus 1 over x squared. Here comes a tricky thing. So you might think that square root of x squared, that's x, but unfortunately that's not quite true. For instance, the square root, if you take square root of minus 3 squared, that's not minus 3. But indeed what it is minus 3. So in this case, what I'm trying to get at, the square root of x squared here, it's the absolute value of x. Okay. However, because x is negative, this becomes just minus x. If x is negative. And indeed, what happens here now, the square root of x squared turns into something quite interesting. So that becomes, again, limit x goes to minus infinity of x times 1 plus 2 over x divided by minus x times square root of 9 plus 1 over x squared. Now the x's cancel out, and you get limit x goes, then you basically can plug in. So this becomes 1 plus 2 over negative infinity, that's 0. You still have the minus, and then square root of 9 plus 0. And what you get is minus 1 over square root of 9, and that's minus 1/3. Which again makes sense. If you ignore this 2, you get x, and if you ignore this 1, it becomes square root of 9x squared, which kind of becomes, 3 times something, and then x over absolute value of x in this case is minus 1, so that's why it should be negative. Negative 1/3. So that's the first technique with dealing with square roots. If you just have a pure square root, you factor things out, but usually square roots come in the form square root of a plus b, and for this we do have a familiar technique that's the same thing for also finite limits, so limits at a point. So question 6. What about the following? Again, still another minus infinity, limit x goes to minus infinity of x plus square root of x squared plus 2x. Well, the trick is, because it's of the form a plus square root of b, the trick is to multiply by the conjugate form. So multiply both sides by x minus square root of that. X minus square root of x squared plus 2x. So a minus square root of b. Because that's just 1, so it doesn't invalidate this equality. And then what you use, it's simply the form a squared plus b squared is, a minus b times a plus b is a squared minus b squared. So in this case, again, just a plus b times a minus b, that's a squared minus b squared. So what we get is now, the numerator becomes x squared minus square root of x squared plus 2x squared, and you have x minus square root of x squared plus 2x. Which simplifies in this case So limit x goes to minus infinity of x squared minus square root squared is just that number. So minus x squared minus 2x over x minus square root of x squared plus 2x. This cancels out. And then the question is, what do you do to the rest? Well, because we've already used this technique, what's left is simply using the previous technique where we just factor out the highest power from the denominator of the numerator and the highest power from the square root. So again, just to clean this up, this is the limit as x goes to minus infinity of minus 2x over x minus square root of x squared plus 2x. And what this becomes, limit x goes to minus infinity of minus 2x over x minus square root of x squared times 1 plus 2 over x. And that's limit x goes to minus infinity of minus 2x of x minus square root of x squared, square root of 1 plus 2 over x. But now remember, same thing as before. Square root of x squared, this time is absolute value of x, which becomes minus x here, since x is negative. So in fact, this whole thing becomes minus x. So in fact, in the end, we get minus x, which becomes plus x. So that's the limit as x goes to minus infinity of minus 2x and then x plus x times square root of that 1 plus 2 over x. And then you factor x out over x times 1 plus square root of 1 plus 2 over x. Now the x's cancel out. And you get simply minus 2 plus 1 plus square root of 1 plus 0, which becomes minus 2 over 2, which is 1. Ta-da! So I think that's what it is. Let me just double check. So minus 2. And then, I think that's what it is. I'm sorry, I forgot about that. Okay. Minus 1. Yeah, okay, I think that makes sense. Okay. Yeah, all right. Sorry about that. Okay, then moving on. So, squeeze theorem. Oh, sorry, I meant to say, let's guess what's next. So, limit as x goes to infinity of e of sine of x over x. So whenever you see sine or cosine, what it is, it's just a squeeze theorem, which says the following. Suppose you have a function g of x that's trapped between f of x and h of x. So if g of x is literally squeezed between f of x and h of x, and moreover, f and h, they go to L. So and the limit as x goes to infinity of f of x equals L, again, finite limit, and the limit as h goes to infinity of h of x, as x goes to infinity of h of x equals L. What this implies is that the limit as x goes to infinity of the middle function is also equal to L. So, and usually you would imagine g being some weird squiggly thing, but f and h are some nice functions. So if f and h, they go to L, this automatically forces g to also go to L. Now what's the idea? The idea is we think of this function as a complicated wiggly thing, and we want to bound it with two much easier functions. How do we do that? With one of the most important inequalities about sine. Well, sine of anything is between -1 and 1. So e of sine of that, it's between e of 1 and e of -1. And then you just divide by x. And lo and behold, you get your function. So this, if you want, is your function g of x. This will be your function f of x. And this is your function h of x. What do we know? The limit as x goes to infinity of f of x is the limit as x goes to infinity of e of -1 over x. So just think a number over x, and that's 0. The limit of the complicated function, h of x, not too complicated. That's the limit as x goes to infinity of e over x, and that's also 0. So you see, here f and h, they have a common limit, namely 0, and therefore, by the squeeze theorem, because though this is squeezed between the two, and the two go to 0, it automatically forces the middle term to go to 0. By the squeeze theorem. And again, write the names of your theorems, that's very important. We get that the middle limit of e of sine of x over x, and that's just g of x, is also equal to 0 as well. So that's just a quintessential way of dealing with limits with sines and cosines. It's usually the squeeze theorem because we have such a nice inequality. Okay, and for the rest, we'll just do 3. So those are really the main techniques of dealing with limits. For the rest, I'll just give you 3 more limits, and let's figure out what technique to use. Number 8, how about the limit as x goes to -infinity of square root of 3x to the 4th plus 3x squared plus 1 over 2x squared plus 3. Okay. This is pretty standard, similar to the previous example, and so, I guess a couple of examples ago, what you do here, you factor out x to the 4th, and then you get 3 plus 3x squared over x to the 4th, so x squared, and 1 over x to the 4th, over x squared, 2 plus 3 over x squared. Which becomes here limit x goes to -infinity of square root of x to the 4th times square root of 3 plus 3 over x squared plus 1 over x to the 4th over x squared 2 plus 3 over x squared. Now here's the important thing. The square root of x to the 4th, right? Think for instance, the square root of -2 to the 4th, that's the square root of 16, and that's 4. you might think, oh, well, of course, it's absolute value of x squared. That's not the same as minus x squared. Like, in this case, what this means, that would mean that the square root of minus 2 to the 4th is minus 2 squared, and that's minus 4. That's not true. X squared itself is positive, so it should just be x squared. And by the way, think about this. Those are positive quantities, so the limit should be positive. It shouldn't be something negative. And then what you get is the limit as x goes to minus infinity of x squared, square root of 3 plus 3 over x squared plus 1 over x to the 4th over x squared 2 plus 3 over x squared. You cancel that out, and I think you just get 3 square root of 3 plus 0, and then 2 plus 0, and that's square root of 3 over 2. Woo! Or I believe if you want cosine of pi over 6, if you want to flex a little bit. Well, again, complete coincidence. It's cosine of pi over 6. And then 2 more, so let's do another ratio. So, limit, by the way, I don't know how black pen, red pen would do 100 limits like that. I'm already exhausted. So limit x goes to infinity of e to the x plus e to the minus x over e to the x minus e to the minus x. So some people may recognize this as tanh, but we don't need to know that. Well, with this, what's interesting is it's a ratio, but there's no x squared or anything like that. Well, just think again of this ln of x example, ln of x squared example. What did we do? We factor out ln of x squared. And that's exactly what we want to do here. So we do limit x goes to infinity. In this case, you want to factor out e to the x. So e to the x of 1 plus e to the minus x over e to the x over e to the x. 1 minus e to the minus x over e to the x. This cancels out, and you're left with the limit as x goes to infinity of 1 plus e to the minus 2x and 1 minus e to the minus 2x. And that becomes 1 plus 0 over 1 minus 0, which is 1. Again, none of that limit. What is happening? This term just goes to 0, and then what's left is just e to the x over e to the x. Last but not least, a limit that's quite interesting in my opinion. Limit x goes to infinity of ln of x plus 2 minus ln of x plus 1. Now, this is infinity over infinity, and it wouldn't really help, infinity minus infinity, it wouldn't really help to factor out ln of x, but one thing you may notice is that you have ln of b minus ln of a, and that is in fact ln of b over a. So what this is, it's the limit as x goes to infinity of ln of x plus 2 over x plus 1. Now, what we want to do, we want to put this limit inside the ln, which is very non-trivial, but essentially what this is called, putting the limit inside the function, is what's called continuity. So because ln is continuous, that's the same thing as saying ln of that limit of x plus 2 over x plus 1. ln continuous. and then you evaluate that limit just like you would do at the beginning. Ln of the limit as x goes to infinity of x times 1 plus 2 over x times 1 plus 1 over x. This cancels out, and what you get is simply ln of 1 plus 0 over 1 plus 0, which is ln of 1, and that gives us 0. Which is hopefully not the points you get at the exam. Hopefully for this question you'll get 10 out of 10. And this was my excursion in limits at infinity. If you like this and you want to see more math, please make sure to subscribe to my channel. Thank you very much.